Thank you, Barak, for that introduction. A little bit more introduction to myself. I'm Apache PMC Spark member, Spark committer since the beginning of Spark. And I've worked on Spark streaming, D-streams before. That was my pet project back in grad school in AmpLab. Now it's gone pretty big. That's incredibly gratifying for me. Now I work on structured streaming. And hopefully, you find the stuff that I'm going to talk about interesting. So the way this deep dive session is constructed is that I'm going to assume a little bit of that you're familiar with the basics of structured streaming and the basics of Spark SQL, basics of Spark data frames, and I'm going to take it off from there. Actually, that reminds me, actually, how many people here, can I see hands who are familiar with Spark data frames? Ah, everyone. How many people here are familiar with Spark structured streaming? Slightly less. OK, good. In a way, I kind of anticipated that, so I have a kind of brief introduction what structured streaming is and what it looks like. So let's start off. So if you're not familiar with what structured streaming is, it is basically a stream processing platform built on the Spark SQL engine and the Spark SQL APIs. It's obviously fast, scalable, fault-tolerant. It essentially provides rich, unified, high-level APIs in the form of data frames and data sets. So that allows you to deal with complex data and complex variation of workloads. And similar to all of Spark, it has a rich ecosystem of data sources from which it can read and write from. So the basic philosophy with which we built structured streaming is that you, as an end user, should not have to reason about streaming. You, as an end user, should essentially write simple batch-like queries. And it's Spark's job to figure out how to actually run it on a continuous stream of data and continuously update the answer as new data flows in. And the basic realization that we had, and that led to what structured streaming looks like, is that you can always treat a stream of data as an unbounded table. So every record on data stream is like an unbounded input table. Every record is like a row being appended to that unbounded input table. And so now you can represent both batch, that is static bounded data, as well as streams, unbounded data, as tables. And that allows you to express your computations with respect to tables and let Spark figure out how to actually run it either on static data or on streaming data. So on that note, there are a couple of empty seats out, one out here, 3 out here. If people are not nervous about sitting in the front bench, they could come here. Some people are perfectly fine being backbenchers. That's also fine. Anyways, so let's, to have a very brief introduction of what it looks like, let's look at a simple streaming query. Well, simple, but often something this simple actually leads to very complex pipelines, complex code in other streaming systems. But I'll show you how exactly this becomes so simple inside using structured streaming. So let's say you have to set up an ETL pipeline where you're getting JSON data from Kafka. You want to parse it. You want to convert it into a more structured form and write it out into a Parquet table. And of course, you want to get end-to-end fault tolerance guarantees because you don't want any failures to drop data or create duplicate data. So, and here we go. So first step is to actually create a data frame from Kafka. And so you specify spark.readstream, you specify you're reading from Kafka, how to read the Bootstrap servers, which topic to subscribe, etc. And there are multiple built-in supported sources, like files. Also, Kinesis is part of our Databricks runtime. And you can have multiple input streams in the same query. You can join them together, etc. I'll talk about those later. But ultimately, what you get is essentially a Spark data frame. And Spark data frame is a single unified API for manipulating batch and streaming data in Spark. Now, in this case, this particular Kafka data frame looks like this. It has basically a bunch of columns giving all the details of every record in Kafka, the key, the value, their binary values, the topic and the partition from which it came from, the the timestamp in which it entered Kafka, etc. Now that it looks like a table, you can do a standard data frame and table-like operations inside Spark to actually parse it. For example, first of all, the data is binary. I need to cast it to a string, then parse that string into JSON with this built-in function called fromJSON. All of these standard manipulations. And that's this cool thing about Spark, that it comes with hundreds of built-in SQL functionalities that are designed to be simple to use and standard semantics and incredibly fast to execute, because we do all the underlying fancy code generation, etc., to make them really fast. Finally, now that you have the parse data, you want to write it out to a Parquet table. So that's where you specify the format Parquet, the path to which you're writing to, and there are built-in support for files, Kafka, and you can add your own arbitrary logic to write it out to arbitrary data sources by this thing called for each, where you can do whatever operation you want on every record. And then finally, you want to specify how to exactly run this query, which is I want to trigger it every 1 minute. I want it to checkpoint all the information, all the metadata and data, whatever needs to checkpoint to restart from failures into a given location. This should be something like HDFS or S3 or Azure Blob Store, of something fault tolerant, and then finally I call start. And when I call start, what happens is that internally Spark essentially translates this code into a logical plan, which is an abstract representation of what the query does. Then it converts it to a much more optimized plan where it figures out exactly what sort of optimizations can be pulled in, how to generate the code in the most optimal form given all the built-in functions that you have used. And then from that template of an optimized plan, it generates a continuous series of incremental execution plans. So as there is new data comes in, it breaks it into micro batches and processes it and writes it out to the Parquet table. So it is essentially Spark's job to figure out that this very batch-like query that you've written, that you could have run it on a batch data as well, but since you're asking Spark to run it on a Kafka stream, Spark will automatically figure out how to run it incrementally on the streaming data. And with checkpointing, you get complete fault tolerance guarantees, because what it does is that at the beginning of every micro batch, it will write out the offsets from Kafka it is going to process into a write-ahead log, so that in case of any failure, it can exactly reprocess the same range of data in exactly the same deterministic manner. So you get end-to-end exactly one's guarantees. And so with this few lines of code, what you have is essentially an ETL pipeline where you're reading from Kafka and writing out to Parquet, and essentially your raw, unstructured binary data encoding JSON is now available in a structured Parquet format within seconds. And of course, you would have some of the standard problems that Michael was talking about in the keynote, the small data, small files, etc. But that's where Databricks Delta comes in, because if you write it to Databricks Delta, you can solve all those problems. But even with Databricks Delta, with Parquet, you get the benefit of the structured data being available within seconds. And we can do this really fast. For example, you should take a look at our blog post where we did a benchmark with other streaming systems, where we showed that we could do 3x faster than any other system, which translates to that you need 3x lower number of machines, 3x cheaper for you to run your ETL pipeline. Anyways, this was a very brief introduction. Now let me start into the meat of the conversation, meat of this talk, where I'm going to talk about stateful stream processing. So let's start from the very basic on what is stateful stream processing. But to understand that, let's first understand what is stateless. So imagine this previous ETL pipeline where you are taking every record, parsing it out, writing out to a table. You are essentially doing something purely stateless because each record needs to be you're processing each record individually without combining information across any other record. So you don't need to remember any side information to process the records. In contrast, in stateful stream processing, let's say you are counting the number of records that you have parsed or maybe additionally filtered, then you're essentially combining information across multiple records. And to do this, you need to essentially maintain some information on the side. For example, in this case, the running count. That is essentially the state. And some of the major challenges of doing stateful stream processing is that how do you make sure that this state, that this information you're keeping on the side is fault tolerant? And how do you figure out that when you're restarting, if there's a failure, you're restarting your query, how do you load the exact same version of the state where it failed and things like that? So this is some of the essential challenges of building a distributed stream processing platform. In structured streaming, with our macro-batch processing, the way it works at a high level is that as you're creating this series of incremental execution plans, each execution plan essentially knows what version of the state it needs to read from. So as each micro-batch reads the previous version of the state data, the previous running count, updates it, and creates a new version. And each of these different versions essentially gets checkpointed out into the same checkpoint location that you have provided, where the Kafka offsets are written out. Now, and with this, the fault recovery becomes absolutely seamless and synchronized with the offsets, etc. So it knows exactly where it can restart from. Now, from the concepts to the actual physical layout, the way this state is stored is actually in Spark's executor memory. So if you're not familiar with Spark's architecture, there is a driver node, and there are multiple worker nodes, which are more actually correctly called executors. And these executors are the ones that run the tasks that needs to, that processes the data. And the state is stored in the memory of these tasks. And as these tasks are launched for each microbatch, the state is updated, and any changes to the state are versioned and checkpointed into GetDFS into the whatever checkpoint location you have provided. So overall, it gives the same exactly once fault tolerance guarantee as stateless computations. Anyways, this was a very short introduction of how exactly state works physically. Now let's talk about how you can actually what is our philosophy of exposing this state to the end users to act in the form of stateful operations? Now, in the data frame API, there are a number of stateful operations, which can be roughly categorized into two categories. There are stateful operations that have automatic state cleanup, and then there are stateful operations where there are user-defined state cleanup. Let me elaborate. So for operations, which are standard SQL operations, the semantics of the operation is absolutely clear. For example, if you're counting, then you know exactly how much, what it means, what it means, and when your data and the state data is old enough that you can clean up and stuff. It knows, you can reason about all of that and automatically clean up old state. Whereas, for arbitrary non-SQL-like operations that you may want to do, the state cleanup is not automatic, because what we want you to do give you is essentially the full power of stateful operations, so that you can control precisely what to keep, what to throw out, etc. And I'm going to, the rest of this talk, I'm going to explain all of these, so hold tight. So to give a very high-level overview, the aggregation, deduplication joins have automatic state cleanup where you really don't need to worry about state, and you can just specify watermarks, and the Spark will handle everything else. And then there's, for arbitrary stateful computation, there's MapGroupsWithState, flat MapGroupsWithState, where you have full control on doing state cleanup yourself. And so the rest of my talk is going to be basically explore these built-in stateful operations, how to use watermarks to do automatic or custom state cleanup, how to build these arbitrary stateful operations, and finally, and probably the most important, how to monitor and debug these stateful operations. So the way I'm going to construct this is that at roughly the end of the session, I'm going to stop at some point and then continue from there. So let's see, in whatever time is left in this session, let's see how much we can, of this talk we can cover. So the first step, and the simplest one and the most used one, is streaming aggregations. And you already saw the simple count as an example. You can also aggregate by key. You can aggregate by a window on a timestamp inside the data. So that is essentially you're aggregating by the event time. And you can also aggregate by both some arbitrary key and the event time. So as you can see, the aggregating by event time is simply just applying a window as if the window is additionally another key. And you can specify the window length, in this case 10 minutes, also the window sliding interval that I want to aggregate by windows of 10 minutes moving every 1 minute, things like that. And of course, there are built-in aggregations. There are, you can write your own custom arbitrary aggregations, user-defined functions and stuff. Now, with these windowed aggregates, what happens is that the way this is constructed, it very naturally and takes care of late data, because for every aggregate window, it's like a bucket. As soon as you receive data for a particular new time window, let's say for the next hour, you automatically open up that bucket and start counting the number of records falling in that bucket. And now these buckets stay open. So even if a data that comes maybe 5 hours late that belongs to a bucket 5 hours old, it will just go ahead and update that bucket by incrementing the count of an old bucket. And that's what's happening in this timeline, that even if data comes in late, it just happens to update an older bucket. But with this, the size of the state will continue to increase indefinitely, because you really don't know when a bucket can be closed, because practically the query is not going to receive data that is maybe 5 days old. So, and to specify that information to the streaming query, that is where we have watermarking. So watermarking is essentially a moving threshold of how late the data is expected to be when we drop, and accordingly the system can drop the old state. So the way it is defined is as follows. So imagine at any point of time in the data you have seen the event time inside the data, you have seen the max event time as, let's say, 12:30 p.m. right now. This watermark, which you specify by specifying this trailing gap, say 10 minutes, is essentially a moving threshold behind the max event time. So at this point of time, when the max event time is 12:30, the watermark would be 12:20. And the engine automatically tracks this. And so what happens is that data that is older than this watermark will be automatically dropped. So let's say your data may be suddenly, a very small fraction of the data may be older than 10 minutes, but the data is already too late for you to take any decisions on it, so it will automatically drop that data. And any data that is late, but not later than 10 minutes, would be allowed to aggregate. So the buckets I was talking about would essentially be kept open for that 10-minute duration. But any data that is older than that will be dropped, and those buckets would be automatically closed and cleaned up, because the corresponding count is not going to change anymore, because any data later than that threshold, we're going to drop it anyways. So that's how the state cleanup happens automatically in aggregation. That's a good question. Let's talk about it offline. Let's hold all the questions to the end of the second session. Okay, so to do watermarking, all you have to do is just call this thing called with watermark on your data frame, specify what is the event time column, and then specify the watermark delay, and that's it. Now, for streaming queries, which does not have any stateful operation, this essentially is completely ignored. For non-streaming queries at all, for like if you write this data frame operation in a batch query and apply it on a batch data, then it just is completely ignored as well. So you can always add this, and then your query, if it's running on batch data, it'll work. If it's running on streaming data where there is actually delays, it'll work as expected as well. And at runtime, when the engine would automatically scan all the data and figure this out. For example, it'll automatically figure out what is the max event time the system has seen. and accordingly calculate the watermark threshold, which is the red line. And then as new data comes in, it'll keep increasing the event time max. Some data may be late. If it's later, if it's earlier than if it's newer than the threshold, then it will be considered. If it's older than the threshold, it will be dropped. So there's a blog post that I've written that explains this in much cleaner detail. So please take a look at it if you want to understand a little bit more. So now the cool thing is that this watermark is essentially a parameter that you can tweak to trade off between how much late data to consider and how much state to keep. So if you want your application to handle a larger amount of delays, like 10 minutes is not enough, I have to consider data that was up to a day late, then you have to incur the cost of keeping larger amount of state because you're keeping more buckets open essentially. And and vice versa, that if you cannot afford to keep that much state in memory because of price concerns, then you have to do that trade-off of not keeping that much late data, not considering later. So this is a knob you can tweak for that trade-off. The next one is streaming deduplication. And this is actually exactly what it sounds like. You have a stream of data coming in. Events in that data has a unique identifier, and you want to essentially deduplicate based on that identifier, in this case, the unique record ID. And so all you need to do is say drop duplicate, specify that unique column ID, and what internally Spark will automatically do is keep all the past unique identifiers that has been seen in the stream, and if any record matches with the past identifier, it will drop that because that record has already been seen. So that's drop duplicate. But again, you don't really, the system doesn't know when it is safe to drop old state data. So what you can do is essentially specify the watermark on the timestamp column and also specify timestamp as another unique column. Now, this works only when you know that the duplicate record is going to have the same exact record identifier as well as the same record timestamp unit. So this is typically the timestamp that is generated at the source that is creating the record, and maybe the duplication is happening in somewhere while writing to, let's say, Kafka and stuff. So typically, using the Kafka arrival timestamp may not be the best idea because that is not what is creating duplicates, or the duplicates are not being created between Kafka and Spark streaming, but duplicates are probably being created somewhere upstream of Kafka. So you have to use the timestamp that is present in the data when the data is being generated uniquely. Same place where the unique record identifier is being generated. So there's some little details to keep in mind when using watermarks with streaming deduplication. Anyways, so let's start where we left off. We did streaming aggregations, we did streaming deduplications. Now comes the more fun ones, like streaming joins. So Spark has supported stream batch joins, basic joins between a streaming data set and a batch data set since the beginning of structured streaming, like Spark 2.0. But in 2.3, which was the previous release a couple of months ago, we started supporting stream joins. And to understand what stream joins is and how it works, let's start with a very canonical example of ad monetization. Basically, you have a stream of ad impressions of when the ad was showed, and you have another stream of ad clicks on who clicked on which ad. And essentially, you want to join them by a common ad identifier so that you know that which impression of the ad led to a click, therefore someone needs to pay someone else. So now this conceptually, while it's a simple idea, the real complexity comes because of delays in when the impression arrives and when the click arrives. So most of the time, the click is likely to arrive at your data center or your application after the impression, after the ad was shown, because it was generated after the ad was shown. But sometimes due to delays, what happens is that the impression may arrive much later after the click. Random things happen. Now, to deal with these random delays, the the streaming app needs to essentially buffer the clicks and the impressions for a sufficient duration so that it can be sure that it sees when there actually is a successful join, that is when there is actually a click and a corresponding impression. So to do this sort of buffering, then it is naturally a stateful operation, where the state is essentially the buffer of add impressions and clicks. And so let's see how to actually express this using data frame joins. So let's start with a simple inner join. So you have impressions, which is a streaming data set or data frame, and joined with clicks, which is another streaming data frame data set. And you're saying that the click add ID should be equal to the impression add ID. That's it. What the system will automatically do is it will buffer all the past clicks and all the past impressions such that it can match. But again, similar to streaming aggregation, if it has no idea when data is actually old and can be thrown out, the state is going to continue growing indefinitely. So to allow some of the buffered data to be actually dropped, you need to provide in this query additional time constraints, just like watermarks, but this requires some additional stuff, and that's what that's what makes this very interesting. So these additional time constraints can be like this. So let's assume that your impressions can be at most 2 hours late because of delays in the network and stuff like that. Now you can express that as impressions with watermark 2 hours. Similarly, clicks, let's say, can be 3 hours late because of, again, same network delays, etc. And express in the same way, clicks with watermark 3 hours. Now, this is the most interesting part. Let's say that a click can occur only within 1 hour after the impression. That puts a very hard constraint on when a click can match with an impression. And this is important because this is what allows us to actually define when a buffered click is not going to match with an impression anymore, and vice versa. So this essentially is like a range join, and this what Spark will do is it will parse these equations that click time is more than impression time, or to put it simply, click time is between impression time and impression time plus 1 hour. And what it will do is it will automatically figure out that essentially impressions need to be buffered for at most 4 hours. Because if you do the math, you can figure out that 3 hour late click may match with impressions received 4 hours ago. I mean, you have to do this math to figure out which Spark automatically does it for you. And figure it out that impressions need to be buffered only for 4 hours, and clicks need to be buffered only for 2 hours for executing the join correctly. And any event that is older than that particular threshold will be automatically dropped by Spark, and any buffered event will automatically be cleaned up. And this is the magic that happens automatically. All you need to provide is this additional constraint of a couple of watermark delays and the time constraint between the left time and the right time bounded in both directions. That left time should be between certain right time and certain right time plus something in that equation form. So, and we also support outer joins with time constraints, but the difference with the inner join is that in inner join, specifying those watermark and time constraints is optional. If you don't specify it, that's fine. It's just your state will keep growing indefinitely. For some use cases, that is fine because state is small, etc. But it is optional. But in outer join, it is not optional. You have to specify the time constraint and the watermark constraint for this. And this is because in outer join, if you remember what outer join is, if a row does not match, let's say it's a left outer join. So if the left side input record does not match with any right side record, it needs to be output as left side and null. So to generate these null inputs, there has to be, the system has to figure out when it can say that a record is never going to match, so I'm going to output it as null, which means that you need to specify these time constraints. But the side effect of that also is that those null outputs gets produced at a delay because the system needs to actually wait for the certain period of time, let's say around the watermark delay, the 2 hours and 3 hours that you specified, to be sure that there is not going to be any further matches for that record. So this is what the difference between outer join and inner joins are. Anyways, both of these are available in Spark right now. You can just use it. All the state management is magical. Automatic state cleanup and dropping of late data. Now, the final operation that is going to talk about is the arbitrary stateful operation. So if you cannot express your computation in the form of a SQL operation like join, aggregation, deduplication, etc., then this is your final result. And this is essentially like jumping down to native code after you have used Python, Scala or Python. You have to do your own memory management, essentially, but not that low. Typical uses are like user tracking, sessionization, where you want to basically track, let's say a user has come to your website and is clicking on stuff, and you want to track the user's movement to understand what products the user may be interested in. So to kind of simplify the problem, let's say you want to track user actions, logins, clicks, and stuff, and you want to essentially maintain the current user status on what the user is currently actively doing. Is it online? Is it active? Is it inactive but online, etc. So let's use this example application and understand how we can solve this. And the solution to all this is these two operations that we provide on data frames called MapGroupsWithState and the more general version of flat MapGroupsWithState. So I'm going to start with the MapGroupsWithState and kind of generalize it further. So it's been available since Spark 2.2, but currently it is in Scala and Java only, and because for writing this complex code, you need the type safety, and that we can provide in Scala and Java only right now because of obvious reasons. So it is currently available in Scala and Java only. So again, reminder that this is essentially the second type of stateful operation where you have no automatic state cleanup or dropping of old data. You are in full control of all of this, and therefore you need to do all of this explicitly. And so you can add watermark to understand what is the progress of event time in the query, but no late data will be dropped based on that watermark. So you have to figure that out yourself. You have to drop it explicitly. And for those people who have used dstreams, MapWithState, and UpdateState by key, this is a far more powerful version of that and a far more efficient version. So let's start. How do you use MapGroupsWithState? So I'm going to break it down into a few steps. And this is how you should think about your problem. So step one, define your data structures. So what is the input event? It's a bunch of user actions. Let's figure out what the data structure looks like. It has a user ID. It has some action. Then what is the state you want to keep for every user, which is essentially the user status. And again, user ID, let's say you just want to track whether he's active or not. And what you want to output. Now, this can be different from the user status, but let's keep it simple. Let's say every time I update the user status because there is some new event for that user, I'm going to output the latest user status for writing it some other place. Okay. Step two is define your state updating function. Now, this function essentially needs three inputs. One is the grouping key, which is the user ID, because that's what you're grouping the whole thing by. It is a generator of new data, new user actions, and what was the previous state, which is, in this case, the previous user status. And using these three inputs, you can compute what the next status is going to be based on the new actions that you have received. And it's Spark's job to actually call this function over and over again for every group as new data comes in. So gives it the function, you define what to do when there are new actions for a particular group. So you get the previous user status, update the status with the new actions, explicitly say that this is my updated state, and then in this case, return the status, the updated status or previous status, whatever you want. So, And then the final step is obviously take this function and stick it inside the data frame operation MapGroupWithState. So you're grouping by the user ID and then saying map the group with state using this function. So now again, as with all other data frame operations, it works with both batch and streaming data. In batch query, it essentially has no prior state and will not going to use any updated state ever because everything is called on the function with all the data for each group. So it's essentially boils down to something like data frames map groups. That's it. But it completely works. So you can use static data to test your map grouping function as well as run it on streaming as well. So now, what happens if, since you don't have any state cleanup or anything, you have no idea when to actually clean up the state. Let's say, for example, the user was inactive for a long period of time. Practically, he has essentially been signed out. So there was no event from the user because he did not click sign out. So what happened? How to deal with that? And that's why we support timeouts. And there, when a group essentially does not get any data for a substantial period of time, then the function that you've provided will be called again. That is, when you're hitting the timeout, the function will be called again, except the new actions, the second parameter of the iterator of user actions will be an empty iterator. And so using, but when that function is called with an empty iterator, essentially you can do whatever action is needed to essentially sign off that person and say, and clear off the state because you don't want to track that user anymore because he's not active anymore. So now there are 3 types of timeout supported. Well, essentially 2 types, but you can choose not to have any timeout, or event time timeout, or processing time timeout. So the event time timeout essentially uses the event time in the data, and processing time timeout uses the wall clock time of your cluster, essentially. Now again, timeouts completely ignored if you run the MapGroupWithState as a batch query. How to use event time timeout is basically you just specify the event time timeout as the type of timeout for the entire query. And you have to enable watermarking because that's what is going to track the event time and use that. And then inside the mapping function, you need to actually, for every group, specify the timeout duration. So the event time timeout as a type is for the entire query, like across all the groups, whereas the timeout duration can be specified to be on a per group level. So depending on maybe the type of user, you could have a 1-hour timeout or a 10-hour timeout. So premium user versus freemium user. You can think of use cases more than me. So you need to specify that. And then when timeout actually happens, you can detect that by this handy methods called has timeout and stuff. And when it has actually hit the timeout, then you can just clean up the state and by saying state.remove. But if you haven't hit the timeout, then every time the function is called, you need to specify the timeout. You need to kind of reset the timeout because the timeout is kind of cleared every time new data is received. So that's something you need to keep in mind when you're using timeouts. And the way the event time timeout works is that the watermark is calculated based on the max event time, et cetera, across all the groups. When one particular group does not receive data, but the watermark has moved for the timeout duration for that group, then the function will be called on that group with has timeout set to true and an empty iterator and stuff. Otherwise, the function will keep getting called with whatever new data, and every time the function is called, the timeout that you set previously is reset, and you need to set it once again. So that, and this is designed such that you have full control every time to update the timeout based on what your current state is or user status is and stuff. The processing time timeout is actually far simpler, where you just wait for the wall clock time if a particular group has not received any data for that time period in the wall clock time, in real world time, then do whatever is needed. Same, the function will get called with empty iterator and has time.set to true. But it's important to remember that this is strictly dependent on the wall clock time. So if it so happens that your query failed, or you stopped the query and restarted it 1 hour later, then you will see a whole flurry of processing time timeouts because it was down for 1 hour. So things must have timed out. And that's the semantic. So you have to pick and choose what you want, in what type of timeout you want. So this was MapGroupsWithState. The flat MapGroupsWithState is essentially a generalization of that, where in MapGroupsWithState, you basically have to return one object. In flat MapGroupsWithState, you can return multiple objects in the form of an iterator, which can also be empty. That is, you may want to update the state and there is nothing worthwhile returning, so you may choose not to return anything in that particular function call. So that's essentially the generalization and stuff. There are other more detailed things that are present, like things like output mode, where it gives actually a little bit more information about what your function is doing. Is your function, the items that your function is generating, are they like new rows being appended, which is essentially the append mode, or are they like each item inside what is returning is essentially like updating the previous value? And based on that, you can essentially, the engine can figure out how to optimize the query and how to write it out to external systems. Should it continue to append all the rows, or should it update out into an external storage system and stuff like that? So these are, again, the super advanced stuff, and please look at my blog post for really understanding these and stuff. So anyways, these are all the stateful operations. Hopefully you understood it. Please play around with it for better understanding. There's obviously the programming guide and their blog posts to actually explain some of these in more detail. So the next step is how to manage these streaming queries. And the question that I often get is that, how do I figure out what is the right cluster size, what is the number of shuffle partitions? So all of these are essentially partitioned by key. So the number of shuffle partitions matters. And setting the number of shuffle partitions in this sort of streaming query has a slightly different optimization function than setting the shuffle partitions for a batch query. And this is because of the stateful operation that needs to be done. It needs to write it out to HDFS, etc., which has additional per task overheads, which doesn't exist in a batch query. So the recommended idea is that set the number of shuffle partitions to 1 to 3 times the number of cores that in your cluster. If you set it too low, then you're not using the cluster enough. If you're setting it too high, like 10 times the number of cores, then what may happen is that the per task overheads start building up and your latency will increase. But again, all of these are knobs that are flexible, then you have to tweak it. Let's say you want to do auto scaling, in which case you have to set the shuffle partitions in terms of the maximum number of cores the auto scaling cluster is expected to have. And if the load is low and it scales down, then maybe slightly higher latency because there are more tasks per core, etc. Those are some of the things you need to tweak when you're actually have developed your application and you want to essentially optimize it for production use. The other thing you need to worry about is the total size of state per worker. And so the larger state leads to essentially higher overheads for snapshotting, JVM, GC issues and stuff. Now, to understand what is the total size of the state, you can monitor the state of the query state. So there are a couple of ways. One, you can actually get the current state of the state, like how many state keys, what is the memory used, etc., just by using the query handle and saying query.lastProgress or query.recentProgress, which gives you a JSON or got a struct of a lot of metrics, including rates and stuff, including the current state of state operators, how many rows in the state. Or you can do it completely asynchronously using by writing your custom streaming querying listener, which is an interface by which you can, for which you can write a custom implementation and register it, and the engine will automatically call your implementation with the latest progress information, asynchronous as the query is running and making progress by running microbatches. In Databricks, though, a little bit of a plug for Databricks here, this is automatically inside the Databricks notebooks. As soon as you start a query inside the Databricks notebook, you automatically see those streaming metrics right inside the cell that you have started. So this, we have made it much easier for you to monitor your streaming queries. Now, if you want to dig a little in more detail than how many total state keys and stuff, let's say you want to find out, is your state skewed in any way, which is causing problems? Is writing the state out to an external storage like HDFS or S3 extremely slow? Is that what sort of those lower level details? And you need to resort to the Spark+AI in the SQL tab, which shows the full details of all the metrics of the SQL plan that is running, and that has all lower level details. Now, actually, a bunch of you already asked how to deal with very large state, like hundreds of millions of rows. So in the default implementation inside Apache Spark, the state data is essentially kept in the JVM heap, which translates that to the fact that when you have millions of keys per executor, you can have GC issues like arbitrary GC pauses and in the worst case, ooms and stuff. So you have to basically configure your Spark cluster in the right way, either partition and distribute it further in a larger cluster, etc., so that the expected size of the state per executor is within the limits of what the executor can handle. And what may happen is that you will see these very large spikes because of GC issues and stuff. Or the solution that we have inside Databricks runtime is you can manage state with RocksDB, where basically instead of keeping the state inside the JVM heap, it is kept on RocksDB running inside the executors, which essentially instead of using just memory, it uses memory and local SSD efficiently. But it also in our RocksDB-based state management solution, it writes it out to HDFS in the same way, giving full fault tolerance guarantees as the default implementation. And please look at the Databricks docs for more details on how to use RocksDB. Anyways, I'm coming very close to the end of my talk. So a little bit about what the future looks for us. So a major initiative right now that is happening in structured streaming is continuous processing, which we announced in Spark 2.3 as an experimental release, and it actually can give millisecond level latencies by running it not in micro batches, but in actual true streaming fashion. So this is one of the next big thing that is happening in structured streaming, and we're going to push towards this, and and my colleague Jose is going to talk more about it today at 2 p.m. Please go and learn about continuous processing with that talk, and we've also blogged about it. So, and this affects all these stateful operators as well, because we want all of these shuffle and stateful operators to work with continuous processing mode, which in Spark 2.3 it doesn't, so we are working towards supporting all of them. So that is something is what is exciting us right now, and that is keeping us really motivated and passionate about providing millisecond level latencies even for stateful operations. More information is on the programming guide, Apache programming guide, Databricks docs. Please look at our blog posts for more detailed deep dives into each of these items. And if you want to learn more about just the basics, like more about what sources are supported, what things are supported, how to use those, please take a look at my previous talk on the basics of structured streaming, where I talk about Kafka, Kinesis, etc.